My name's Chad Merkin. I'm the director of the IIN, something that obviously we're very proud of. And I want to welcome you to the 13th annual symposium. This has been an event that has been building momentum through the years. Every year seems to be bigger and better, and this is no exception. And in large part, that has to do with the people that we attract to campus and the incredible group of speakers that we have lined up for you today. Now, we've had obviously a lot of exciting news, and we've adjusted the schedule today because we've got the good fortune of sharing with you, of course, the news firsthand of the Nobel Prize, and in fact the winner here, or one of the winners here, to present to you and talk a little bit about that incredible accomplishment. To introduce the speaker and our special guest, I'm going to invite Sam Stoop on stage. Sam's been a great partner in the development of nanotechnology at Northwestern. He's the Board of Trustees Professor of Material Science, Chemistry, and Medicine, and Director of the Simpson Query Institute for Biomedicine. And he will take a few minutes to share with you some of the facts about our special speaker. Thank you.
Well, thank you, Chad. Good morning, everybody. So as Chad mentioned, we did get very exciting news yesterday. So in the wee hours of the morning, Wednesday morning, probably around 4 a.m., the Royal Swedish Academy of Sciences announced that Northwestern molecular nanotechnology pioneer, Sir Fraser Stoddart, was being awarded the 2016 Nobel Prize in Chemistry. He shared the prize with Jean-Pierre Sauvage from the University of Strasbourg, who actually has been a frequent visitor at Northwestern, and Ben Faringa from the University of Groningen in the Netherlands. The Swedish Academy awarded the Nobel Prize in Chemistry this year for the development of the first examples of molecular machines by these three outstanding scientists. So imagine, I guess it's difficult to understand what a molecular machine is, but now imagine a dumbbell, the type that you use at the gym when you're working out, and you have these two giant heads at both ends. And then by the magic of chemistry, a tiny ring gets threaded onto the dumbbell. Now it's trapped, can't get out. And so, but it can shuttle to different positions, desperately trying to get out. So this is not a bond between the dumbbell and the ring, not a chemical bond, but it is a mechanical bond. So this shuttling by design can emulate, for example, the function of a switch. It can also, in other forms, create a molecular construct that actually expands and contracts, emulating the function of a muscle in our bodies. And yet other forms, we might even think of emulating the functions in a computer chip. So Fraser has been a pioneer in this very exciting new field in chemistry. And he has been particularly a pioneer in the fundamental understanding of how these molecular constructs can behave as machines. Now, like so many scientists in the US, including me, Fraser is an immigrant. And he was brought up in Edgelow Farm in Scotland, where he did not enjoy, I mean, I've heard this from him many times, the joys of electricity until he was 17 years old. He received his early education at a local village in Scotland before going to Melville College in the beautiful city of Edinburgh. And he received all his degrees from the University of Edinburgh. Now, moving forward, several decades of great achievements and recognition. About, I think, 8 years ago, Chad Merkin and President Emeritus Henry Bienen were instrumental in wooing him to Northwestern from UCLA, where he was my alma mater, if I may say. Since that time, since he joined us, since we were lucky to have him as a colleague 8 years ago, he has been a very important member of the faculty at IIN and member of the steering committee and has done lots of things for the development of IIN. I don't have the time to tell you about all the honors and awards that he has received. They have come from around the world, all continents almost, and of course here at home he's been honored, and in his homeland he's been honored by the Queen, right? So Queen Elizabeth honored him as well. And you can go to the web if you would like and enjoy learning about all the awards and recognition that Fraser Stoddart has received. What I want to tell you briefly is the things that you won't find in the web. And so the fact, is that he's not only a brilliant scientist. I know this firsthand because I have worked with him, I have published with him, I have had joint students with him. But also, he is an incredible human being. As they say in Scotland, he's a mensch. An amazing colleague. He is 24/7 about science, but he's also 24/7 about being a good colleague. He's always there to be supportive. Whenever you need him, he's there. Anyway, I personally have loved every minute that I've interacted with Fraser here at Northwestern over the past 8 years. This amazing ultimate recognition in science could not have been given to a better person. So it's great to rejoice, of course, for what this means to Northwestern, but it is really wonderful to rejoice because it happened to Fraser, the great Fraser Stoddart. So ladies and gentlemen, please help me to welcome the amazing person, my dear colleague, Fraser Stoddart, Nobel Laureate in Chemistry 2016.
Well, thank you ever so much, Sam. I will have to ask you sometime what a minch is. So it's my great honor to be standing here today. I am humbled by the events of yesterday. I'm, however, nonetheless going to try and entertain you for a very short time with a story about being in the fast lane on the road to Stockholm. Yesterday, I made some off-the-cuff remarks. Today, I'm going to be back on message. So, Sam has set the stage. There's the dumbbell that he mentioned in the retaxane. Here is the catenane with two interlocked rings. So it was back at the early 1950s that Professor Frisch at the State University of New York coined the term the mechanical bond. Since there's no covalent bond between the components, the blue and the red here, for example, in a catenane, the linkage has been called a mechanical bond. If we go to the retaxane, and one of the very fundamental messages I've got to get over to you is that this entity is a molecule. Even Wikipedia will get it right. So it's about time that the chemists and other scientists did as well. And again, this is Wikipedia's definition of catenane. And you can see these words come from Latin. Down here, you'll see a very familiar counting device that the Chinese in the audience will recognize right away. And up here, of course, we've just been treated this summer to an event in Rio that reminds you of the Olympic rings. And I parenthetically will say they inspired us to make a 5-catenane back in the 1990s. I won't go into it so much today, but symbolism and art has had a huge influence in my design of my science. You will not be able to read this slide. But what I will point out is that the action, because this is really new chemistry, and the point I want to make today is chemistry is maybe the youngest science of the lot. Don't think about it as the old science, it's the new one. And this is very true in terms of the mechanical bond. So it was round about 1980 that my, 83 to be more precise, colleague Jean-Pierre Sauvage went along a route that took us down here using as a source of molecular recognition to make the mechanical bond transition metals. A little later on, we came along and we went along this route using donor-acceptor interactions. And then here at Northwestern in 2010, we had a major breakthrough in the use of radical pairing, the use of radicals to bring the components together to make catenanes and retaxanes and other mechanically interlocked molecules. Now, I just want to make a comment that history is a habit of repeating itself. When I was an undergraduate student at Edinburgh, we learned about the chair-chair flip of cyclohexane. It was followed by NMR spectroscopy. Later on, at the end of the 80s, we made our first degenerate 2-catenane, where the A and B of these red rings swap places. So the only way you can tell this is happening, as you can with that process up there, is by going to an NMR spectrometer. Likewise, the molecular shuttle, as this ring darts from the left-hand station, if we might call it that, to the right-hand one. So how do you make these molecules? It's really extremely simple once you find out how to do it, but it took a decade to find out. So we take this dication, we take this dibromide, we mix them together in acetonitrile with silver tetrafluorophosphate, wait for a week, and in a modest 32% yield, we isolate this 2-rotaxane, or molecular shuttle. But what I want to get over here, and what the major principle is that is important, is that this leads to so-called template-directed synthesis, where you have this wonderful interplay between covalent, non-covalent, and the mechanical bond. So you start with components that don't even want to know each other. You form one chemical bond, and they want to get together. And they get together by the blue coming and nestling inside the red. Having got to this point, it's downhill. Another chemical bond is formed here, and more of these non-covalent bond interactions indicated by these vertical lines is switched on. But the excitement doesn't stop there, because you realize that you have switched on these non-covalent bonds, and they can be then used to be switched on and off at will. So another representation from 91 of the molecular shuttle, the ring darting back and forth between these two stations at roughly 1,000 times a second at room temperature. And here's just a movie to show you what's going on, not only in the retaxane that I've spoken about that is degenerate, but also in the degenerate catenane with recognition sites. So there are points on the rings where they want to stop and, as it were, interact with each other. Moving on, we had to leave degeneracy and introduce the whole situation that is, again, analogous to putting just one substituent on a cyclohexane ring. You go from an equatorial to an axial component. And notice the very important 2-to-1 difference here. So now we've got two different, we call them conformations. Gottfried Schill, he might be the person who was forgotten by Stockholm yesterday. He's still alive in the Black Forest. He made a huge contribution through what was called covalent directed synthesis. Anyway, that comment apart, I want to tell you, he coined the term translational isomers to describe now two isomeric forms, because a green station and a red station are going to be as different as chalk is from cheese. And that is expressed in this 9-to-1 ratio in each case for a preference for the green station. The green station, incidentally, turns out to be a tetrathiafulvalene site, and the red one, a dioxynaphthalene. I don't have time to share all the structure with you. But here you see a movie that is trying to get the message across about the nature of the switch now. It's spending much more time with the green than it is with the red. Now, yesterday I was bombarded with, well, what's it good for? So in my UCLA days, I had the great good fortune to collaborate with one of the most amazing physical chemists, Jim Heath. And over a decade, working almost seamlessly together, we got to a point by 2007 where this ritaxane could be put into a crossbar device, 40 wires by 40 wires, therefore 160,000 junctions to give us a 160 kilobit molecular memory. Testing of the bits, well, it could only be a very few of them, but that was enough to putting a very high threshold on here, a good bit, to show that at least a quarter of them, those yellow ones here, functioned well. So there was some loss of, if you like, efficiency, but nonetheless, using the quarter, and by this time, our collaboration, incidentally, had started at UCLA, but Jim had moved to Caltech. Actually, I tell a little story here. One day, the Los Angeles Times announced that Gordon Moore of Intel had driven up to Pasadena with his wife with a check for $600 million. This is one of the most remarkable things about the United States. It's this philanthropy that drives very great institutions to have tremendous faculties to carry out world-class research. And so what was the result? I no longer had a colleague at UCLA. Jim took off to Caltech. And so in the ASCII-2 code, here is California Institute of Technology. Molecular RAM at now 10 to the 11 bits per square centimeter. And so if you compare this with the semiconductor roadmap, then it's well ahead of its time. So finally, how do we go from switches to machines? And so this brings us to the Northwestern era, where after thinking about it and looking at what had been done in the literature, I could fairly say artificial molecular switches are a dime a dozen, or 10 a penny. Artificial molecular machines are still few and far between, and this was back in 2012. Machines need to perform work on their immediate environments. Switches don't do that. So assembling and controlling synergistically artificial molecular machines housed in highly interactive and robust architectural domains heralds a game changer for the chemical synthesis and a defining moment for nanotechnology, molecular nanotechnology. And so if you're going to build an artificial switch on the nanoscale, it's a very different challenge from what you would do in the macroscopic scale. So on the macroscopic scale, if you were a physicist and you wanted to carry this particle from here up to there, you just say it's a bicycle. You go over this mountain, down into this valley, over this mountain, and down into that valley. No, you don't do this in a nano world. What you have to do is, starting at the same place, you have to juggle around with the energy wells and the transition states. And this juggling around act is a massive exercise in design. It requires incredible intellectual input, and I've been so fortunate to have around me students and postdocs with the capacity and the ability to design systems that work like this. So we are also inspired by nature. Nature uses the same principles. So here you see bacterial rhodopsin pumping protons across as a result of taking down this transition state, having started over here, to allow the proton to get into the middle here, and having got there, decreasing this transition state to allow it to come out the other side. So could we imitate this action with an artificial system? Here is the dumbbell, and here is the ring. And to cut a long story short, it has a neutral green end and a charged, one positive charge on the right-hand side. The ring has 4 positive charges. And what we were able to show is that you can feed this ring on in a unidirectional way. We can have it come on from the left-hand side and depart from the right-hand side. I don't have time to go into the details, but that was well and truly nailed down and is well recorded. So again, let me show you a movie just to get over the message. On from the left, off from the right. But we've done no work. We take a ring out of solution and we put it back again. So now finally, here is the design of a molecular pump where we can bring a ring on from the left-hand side. And this is where we use our radical chemistry discovered here at Northwestern to attract the ring on, and then having attracted it on, get it to go over thermally this barrier here, over the green door I sometimes call it, and then have a collecting chain to collect the rings. And if we can collect the rings here, then we're going into a high energy state, and we're taking the state away from equilibrium. So one of the big challenges in this area is to do chemistry and science away from equilibrium. And we were able to do this, and I just show you some slides here. The first ring sits round about here, and then the second ring that goes on pushes it over to the right, and the next one sits round about here. So you can actually tell where the rings sit. Another movie, so when you see the change from blue to purple, this is the formation of radicals that attract the rings on to what we call the molecular pump. And what you've seen here is them collecting over there on the right-hand side. We'll just watch it one more time. And you notice how the first ring is trying to come back, but it's prevented from coming back by this green barrier. So just to wind up, what we're doing now is we're trying to be more efficient. We have pumps at both ends of a long polymer chain, and we would like to use light, because that's very clean, sacrificial electron donor, to pump rings on 2 at a time. We would like to be able to do it much faster than we can at the moment, and that's being addressed. And if we can do that, we can create a new form of matter. We can create a polymer with sliding rings on it. These rings don't want to be on the polymer chain. They will dance around, and there's every reason to believe that such molecular species, when rendered in materials, these materials will have rather unique, say, viscoelastic properties. So just a brief look at the progress of this science. As I say, it is new chemistry. It took off in literally 1990. And the interesting thing is catenanes always dominated the field to begin with, but eventually they were outstripped by the rotaxanes. And I'll leave you to work out for yourselves why that might be. Everything, of course, is on a rise. Citations. And the distribution of citations is the familiar situation, great papers and not so great ones. Where is the work done? Well, a lot of it's been done in the United States. But we really have to think about how we keep it going here, because I'm not going to be here forever. And I'm certainly not going to go back there, where there is a lot of activity going on, but heavens, it's under threat, in my opinion, at the moment. Japan, as you might expect, China is catching up. I would say in another 5 years, this will be the darkest green on the map. Okay, so if I haven't been very fluent, if I haven't got the message across, around about the 24th of October, I heard this morning from John Wiley, they will publish a book, The Nature of the Mechanical Bond, From Molecules to Machines. It's a 6-chapter book with an introduction, a couple of chapters on synthesis, a chapter on, chemical topology. This was never mentioned by Stockholm yesterday, but Jean-Pierre Sauvage and I have also teamed up together and put a huge amount of effort into chemical topology. And some of you may recall that on Tuesday, the physicists shared a prize for topology in a physical domain. So I think that was just a little bit of a lost opportunity in Stockholm. However, they'll get an opportunity to make it up. Stereochemistry, and then finally, in the last chapter, from molecular switches to molecular machines, using the mechanical bonds. Now, this was not my doing. I was a very impressed spectator by, and this is where I can link up with Sam's too, Carson Bruns, here he is, was a joint student between Sam and myself. He's now a Miller Research Fellow at Berkeley. He is one of the most accomplished writers, illustrators of science, and he can, well, I can't illustrate the way he can, but he can probably write about 10 times faster than I can. Amazing. And what I would like today to say is Carson is going to be on the market as an assistant professor. And the comment I have is Harvard, MIT, Yale, Princeton, Stanford, Caltech, UCLA, Northwestern, Berkeley. What an opportunity. This man knows more about mechanical bond than I do. Remarkable. And just to finish up, a few images. They represent another 490, roughly, graduate students and postdocs who've moved this story along over 35, 40, 45 years, starting in the UK, then at UCLA, and now here at Northwestern. I do want to recognize a huge amount of funding that I've had in recent times from Saudi Arabia, from the King Abdulaziz City for Science and Technology. Without this major fillip, I wouldn't be standing here today. Thank you very much.